Hello everyone. So in this video, we will be discussing the continuation of the limits involved by indeterminate forms. So previously, we've already discussed in our session some types of the indeterminate forms. So now we'll be discussing other forms of the indeterminate forms. So first, we'll be discussing this form wherein if we substitute our limits to our function, that would give us a 0 times infinity result. So for example, we have two terms in our equation. So if we try to substitute our limits there, or our limit there, we'll get the result of 0 times infinity. So if that's the case, if this f of x is 0 and this would be infinity, you have to change the form into this one, f of x all over 1 over g of x. So again, if f of x would be 0, that should be the value at the top. So our numerator would be the term that became 0, and the g of x would be the term that would be in the denominator. Now, if g of x would be our 0 and f of x would be infinity, that's the time g of x is at the numerator and f of x is at the denominator. Okay, so do not be confused. Again, you just have to select whichever would become 0. So that would be our numerator, and the denominator is the one that becomes infinity after we have substituted the limit. So let's try some example. We have here, evaluate the following limit. We have, as limit of x approaches to 0, we have x ln x. Now if you try to substitute your limit here to our function, you would get 0. X would become 0 because you have substituted the limit for the x. And when you calculate ln of 0, that is infinity. So meaning to say, as you can see, this now takes the form of the indeterminate form 0 times infinity. So since x is our 0, meaning to say x would become our numerator. So x would be here. That is all over 1 over our g of x, which will be ln x. Now let's try again to substitute after we have changed the form. We have to substitute again and see if we can get a constant result other than the indeterminate forms from here. So if we substitute 0 to our x, that would still be 0, and again, if we substitute 0 to ln x, that is infinity. So 1 over infinity, that is still equivalent to 0. So our form now changes to 0 over 0. So this is another form of indeterminate forms that we have discussed last time, which is, if this is the form 0 over 0, we'll be using the L'Hopital's rule. So for the L'Hopital's rule, the rule for L'Hopital's rule is to derive the numerator separate with the denominator. So derivative of x is 1. Derivative of 1 over ln x, so we'll use quotient rule for this one. So ln x, we have ln x times the derivative of 1, which is just 0, minus 1 times the derivative of ln x, which is 1 over x, all over the square of our ln x. So we have ln x squared. Now this would be cancelled. So this would be equal to 1 all over negative 1 over x all over ln x squared. Now, let's try to simplify our fraction. This would become 1 over negative ln squared x over x. So you just have to multiply with the reciprocal of this one. divide the fraction by multiplying with the reciprocal of the denominator. And after that, let's try to substitute our limit again. So if we have 1 here as our numerator, we have ln squared of infinity over infinity. So as we know, this is infinity here. This is another infinity over infinity. And as we know, infinity over infinity, that is still infinity. So that is 1 over infinity. Now 1 over infinity, as we all know, that is equivalent to 0. So meaning to say this is already our final answer. Okay, I hope this one is clear with all of you. Now, let's try to answer another example, which is this one. So, pi over x tan pi x over 2. So, our limit is still 0. So, again, before we proceed with some other alteration of the equation, let's try to substitute first if it would give us a constant answer. But if it's not, then we'll go ahead and transform our equation. So pi over x, as we know, this would be replaced by 0. This would be replaced by 0. Pi over 0, that is infinity or undefined. And if you try to calculate tan pi times 0 over 2, that would give you a result of 0. So meaning to say, the tan term is our numerator because this is the term that became 0 after we have substituted the limit. So that would become our numerator here. So we have tangent of pi x over 2 all over 1 over pi over x. Or that is just equivalent to pi x over 2 all over x over pi. So just the reciprocal multiply with the reciprocal of the denominator. So after that, let's try to substitute our limit again if we can get a constant result from this one. Now, tan pi times 0 over 2, the same as here, it would give you a 0 result. Now, 0 over pi, any 0 divided by any number, that is still equal to 0. So meaning to say, this this resulted to an indeterminate form. So meaning to say we have to use L'Hopital's rule for this one. Now for the L'Hopital's rule, again, we have to derive the numerator separate with the denominator. So the derivative of tan is secant squared. So that's secant squared pi x over 2 times the derivative of pi x over 2, which is pi over 2. So let's just write that here in the front. And we have to derive also the denominator. So derivative of x over pi is just equal to 1 over pi. Now after we got the derivative, let's try to substitute our limit again, which is 0. So pi over 2 secant squared pi times 0 over 2. If you try to calculate that, that would give you pi over 2 all over 1 over pi, or division of fraction, you have to multiply with the reciprocal of the denominator, so that would give you pi squared over 2. So this is now our final answer. So the moment our answer is already not an indeterminate form, so that's the time that we have to stop also. And that is our final answer. The next indeterminate form that we have is the infinity minus infinity. So if you substitute your limit to your function and it would give you an infinity minus infinity value. So meaning to say if your functions are f of x and g of x, and that would give you infinity minus infinity, you have to rearrange your equation to this one. We have 1 over g of x minus 1 over f of x all over 1 over f of x over g of x. Okay? Class, g of x would become positive here. And just do not mind the signs, just take the absolute value of g of x. And for the f of x, just also have it negative for the numerator. So assuming we have this equation here or function, we have as limit of x approaches to 1, we have 1 over x minus 1 minus 1 over ln x. Now if you try to substitute that here, we have 1 here. This one is 1. Now 1 minus 1, that is automatic 0. 1 over 0 is undefined. So let's just have that as infinity. And ln of 1 is 0. So 1 over 0 is also infinity. So meaning to say we have to change the form into what I have shown you earlier from the previous slide. So this is our g of x. This is our f of x. Now we have to change that again into 1 over g of x minus 1 over f of x all over 1 over f of x times g of x. So here we have, let's write the limit. We have 1 all over 1 over ln x. So this is already over 1 and our g of x is 1 over ln x. So we have to all over that with 1 over ln x. Minus 1 all over 1 over x minus 1 all over 1 over 1 over x minus 1 times 1 over ln x. So this is already the altered equation that we have. Now let's just erase this one. And let's simplify our equation first before we continue with the substitution. 1 divided by 1 multiplied with the reciprocal of the denominator, that is just equivalent to ln x. The same as here, that is x minus 1. Again, just to avoid confusion, this is all over, so meaning to say that's 1 over 1 times the reciprocal of ln x over 1. So that became ln x. And the same as here, so that's 1 over 1 times x minus 1 all over 1. So that is x minus 1. So after that, let us combine this one as well. We have 1 over 1 over x minus 1 times ln x. So that would give us ln x minus x minus 1 all over x ln x minus ln x. I just distributed this x times ln x and negative 1 times ln x. So that's why it became x ln x minus ln x. Now let's try to substitute our limit, which is 1. Now if you try to substitute that, that would give you ln of 1, 1 minus 1. This is 0 minus 0. And this one would be 0 minus 0. So that would give you 0 over 0. So meaning to say, that is another indeterminate form. So we have to use L'Hopital's rule. So by L'Hopital's rule, we have to derive individually the numerator and the denominator. So we have derivative of ln x is 1 over x. Derivative of negative x is negative 1. All over derivative of x ln x. So that's product rule. 1 over x plus ln x times derivative of x, which is just 1, minus the derivative of ln x, which is 1 over x. So this is now our function. Now cancel this, cancel this. So what we have left is 1 over x minus 1 all over 1 plus 1 plus ln x minus 1 over x. Now let's substitute again our limit, which is equal to 1. So 1 over 1, that is 1, minus 1, that is equal to 0. 1 plus 0 minus 1, that is just also equal to 0. So meaning to say we have to do another derivative here for our equation, which would give us derivative of 1 over x, that is negative 1 over x squared. Derivative of negative 1 is just 0. And derivative of ln x is 1 over x. Derivative of negative 1 over x is negative 1 over x squared. Now let's try and substitute if we can already get finally a constant value here. Negative 1 over 1, that is negative 1. This is 1 minus 1. I'm sorry, this is already minus, so derivative of negative of 1 over x is negative 1 over x, and since this is minus, so this would be plus. So we have 2. So our final answer now is negative 1 over 2. Okay, so there's a lot of deriving that was included in this equation. So you have to continue deriving so long as you still get an indeterminate form. Okay, so next one is limit as x approaches to infinity x squared over e raised to 2x. So let's try and substitute. So we have infinity squared over e raised to 2 infinity. So infinity squared, that is equivalent to infinity still, and this one would still give us an infinite value. So meaning to say this is still an indeterminate form. Infinity over infinity is still an indeterminate form. So we have to use L'Hopital's rule in this case. So we have limit as x approaches to infinity. We have to derive x squared. So the derivative of x squared is 2x. Derivative of e raised to 2x is 2e raised to 2x, right? And let's try to substitute 2 times infinity, that is still infinity. Again, please review your properties of infinity in order for us to understand why it became infinity. So e raised to 2 times infinity is infinity times 2, so that is still infinity. So meaning to say another derivation, derivative of 2x is 2. Derivative of 2e raised to 2x is 4e raised to 2x. So we still have the limit here, which is infinity. Now, our numerator is 2 because we don't have any variable. The denominator is infinity still. So 2 over infinity, or any constant number divided by infinity, is equal to 0. So our final answer is 0. So another indeterminate forms that we'll be discussing is r 0 raised to 0, 1 raised to infinity, and infinity raised to 0. So given limit as x approaches to a, we have f of x raised to g of x. Perform the following steps. So we have to let any variable equivalent to this, and then we have to take the natural logarithm of both sides of the equation of 1. So we have to take ln both sides in this form. And the limit at this point will take the form 0 times infinity. So if it would become 0 times infinity, we have to change that into the corresponding alteration, which is under 0 times infinity. Now, if the limit would become 0 over 0 or infinity over infinity here, after we have substituted the limit, then we have to apply L'Hopital's rule to the right equation. To the right equation only, not the left equation. Suppose ln of n is equivalent to L. So meaning to say we already have our final answer. So let's try to solve some example which is under the form. So we have infinity. So we have x raised to 1 over x. So if we would substitute our limit, we have infinity raised to 1 over infinity, which is infinity raised to 0. So meaning to say, we have to apply the, the rules stated there. So first was to take or to equate this into any other variable. So let's say, for example, Let's have a, let's have that as y. We'll equate this to y. Y is equivalent to limit of x approaches to infinity of x raised to 1 over x. And then afterwards, we have to take ln both sides. So this would become ln y is equivalent to ln of x raised to 1 over x. And as we know from the properties of natural logarithm, the exponent would become or would be beside the ln. So we have 1 over x ln of x. Then after that, we have to take the limits of this, both sides. So we have limit as x approaches to infinity. No, to the right side only, I'm sorry. So we have ln y is equivalent to limit as x approaches to infinity. We have 1 over x ln x. So this is kind of lengthy. So we'll stop after we can find a constant value. So we have as limit of x approaches to infinity, 1 over x. That is 1 over infinity times ln of infinity. As we know, this is 0, this is infinity. So meaning to say, it already took up the 0 times infinity form. So we have to change the right side also to the f of x over 1 over g of x. So whichever term would become 0, that is our numerator. So 1 over x became 0, so that is our numerator, all over 1 over ln x. Okay? So afterwards, let's try and simplify this one first. So that would become ln y is equivalent to ln x over x. Just divide this 1 over x times the reciprocal of the denominator. That became ln x over x. After that, let's substitute the limit. So ln of infinity over infinity, that is still equal to infinity over infinity. So meaning to say, we have to use or we have to apply L'Hopital's rule. So in L'Hopital's rule, ln x, the derivative of that is 1 over x, and the derivative of x is 1. So basically, after we have applied, let's try to take the limit again if we can already get a final value. We have 1 over infinity all over 1. And as we know, 1 over infinity is equal to 0, and over 1, that is equal to 0. So meaning to say, ln y now is equivalent to 0. Okay, so after that, we have to change or we have to remove the ln on the left side. So we have to raise both sides by e. So that would become ln y is equivalent to e raised to 0. And from the properties of exponential and ln, e raised to ln is equivalent to the function of our ln. So meaning to say that is equal to y is equivalent to e raised to 0. And as we know, y is equivalent to this. So meaning to say, as limit of x approaches to infinity of x raised to 1 over x, that is equivalent to e raised to 0. So, as we know, e raised to 0 is a constant value if you try to calculate that. So, that is already our final answer. And e raised to 0 is equivalent to 1, so you can also have your answer as equivalent to 1. Okay, so I hope this process is clear because I think this one is the most complicated process than the other forms of indeterminate. Okay, so let's try another example which is still under this form. So we have 1 plus 2 over x raised to x. So let's try and substitute our limit, which is infinity. So 1 plus 2 over infinity raised to infinity. 1 plus 0, that is raised to infinity. So that is equivalent to 1 raised to infinity. So meaning to say that is an indeterminate form. Now again, since this is an indeterminate form of 1 raised to infinity, we have to take or equate this into y. So y is equivalent to limit as x approaches to infinity of 1 plus 2 over x raised to x. After that, we have to take ln both sides. So we have ln y is equivalent to the exponent this side, the ln, 1 plus 2 over x. After that, we have to take the limit of the right side. So we have limit as x approaches to infinity of x ln of 1 plus 2 over x. This would become infinity. This would become ln of 1 is 0. So meaning to say, we have to change the form again. So that would become ln of 1 plus 2 over x is the term that became 0. So meaning to say that is our numerator. So we have ln of 1 plus 2 over x all over 1 over x. Okay? So I hope you still remember the form of this one. The f of x over 1 over g of x. After that, let's take the limit again. Let's try to substitute. So ln of 1 is 0. 1 over infinity is 0. So meaning to say, we have to apply L'Hopital's rule again. So this process is just the same, practically the same. So we have to take the limit. No, we have to derive this. Derivative of ln of 1 plus 2 over x is negative 2 over x squared all over 1 plus 2 over x. Now, derivative of the denominator, which is 1 over x, is negative 1 over x squared. So, that is still equivalent to ln y. Now, let's still simplify this. So, we have ln y is equivalent to multiply with the reciprocal of this one. So we have negative 2 over x squared times the reciprocal. Our LCD is x. So our denominator would be x plus 2 all over our denominator, which is negative 1 over x squared. Now let's try to take the limit again for this. And let's see if Now let's try to take the limit later. Let's simplify this one first. Cancel the x, one of the x there. So we have lny is equivalent to limit as x approaches to infinity. We have negative 2 over x times x plus 2 all over negative 1 over x squared. Let's divide this one by multiplying with the reciprocal. So we have negative 2 over x times x plus 2 times a negative x squared over negative over 1. So cancel one of the x here. So what we have left is limit as x approaches to infinity. We have negative 2 times negative x, that is positive 2x over x plus 2. So that is still equivalent to lny. Now let's try substitute our limit here. 2 times infinity is infinity. Infinity plus 2 is still infinity. So we have to apply L'Hopital's rule again. So derive our numerator again. Let's just write our limit. Derivative of 2x is 2. Derivative of x is 1. So basically, our answer is 2 over 1. Now we have to remove the ln. So we have to ln raised e both sides. So we have e raised to ln y is equivalent to e raised to 2. So y is equivalent to e raised to 2. And since y is equivalent to this, so we have limit as x approaches to infinity of 1 plus 2 over x raised to infinity is equivalent to e raised to 2. So meaning to say, our final answer is e raised to 2. Okay, so I hope this one is clear with all of you. Just repeat repeat watching the video if you are still unsure and confused. Okay, I hope this video helps. Thank you, and I'll see you on the next session.